Hey guys, welcome to Tutes Online. Today I'll be providing you with an introduction to transformers. Transformer is a piece of equipment which is able to transform, that is, increase or decrease, the voltage or the current in a circuit. The transformer is only able to transform a time-varying voltage or current, so that means it can only transform AC and not DC. So your voltage source here must have a certain frequency. For America, this is 60 Hz, and for pretty much the rest of the world, it's 50 Hz. Most transformers are made up of a large iron core, which looks something like this, and it's got an input known as the primary winding. So this is a cable just wound around the iron core. This is our primary. And so this here has a voltage Vp and a current Ip. The current's going this way. And there's an output known as the secondary winding. So this has its voltage Vs and a current Is. So using the right hand grip rule or the corkscrew rule, if this is the current, we know that the magnetic field will be going this way. So our magnetic field is going around here. And so adding up all the windings, the magnetic field adds up and flows through the coil this way. And it follows the iron core this way, and it connects back up. And this flowing magnetic field, the magnetic flux, is given the symbol phi. So the magnetic flux is flowing through the secondary winding, and you can see it's producing a current in this coil, which is going this way. And this comes from Faraday's law. Which says that a change in magnetic environment of a coil will cause a voltage, or EMF, to be induced in the coil. So our EMF, which is our voltage, is equal to minus N d phi dt. This N is simply the number of turns in the coil, and this minus here is Lenz's law, which says that the EMF, or voltage generated by the changing magnetic flux, will be the opposite polarity to its source. So this current is producing a magnetic field opposing this magnetic flux. And finally, this d phi dt just means that the magnetic flux, phi, needs to be time varying, not constant, and that's why we said we needed AC. Because if this was DC, that would be a constant value, so you'd have minus n times by 0, the differentiation of a constant, and so your voltage induced would be 0. So the current on our secondary here is going to be proportional to our primary current. A higher input will lead to a higher output. This is also true for the voltage. But the secondary current and voltage is also dependent on the number of turns you're using in your transformer. So we know that the power is equal to our current times by our voltage. So you can't just increase the voltage on the secondary and keep the current the same, otherwise you'd be increasing your power. So if you increase your current, you have to decrease your voltage, or vice versa. This means power in is equal to power out, ignoring any losses. So the formula for a voltage transformation is Vp over Np equals Vs over Ns. That is our input voltage over the number of turns on our input winding is equal to the ratio of the voltage on the secondary over the number of turns on the secondary coil. So having less turns on the secondary side will give you less voltage, However, this means that the secondary side will have a higher current. So as you could guess, the formula for the current is IP times by NP equals IS times by NS. A transformer which increases our voltage is known as a step-up transformer, and one that decreases the voltage is known as a step-down transformer. Even though technically a step-up transformer will decrease the current and a step-down will increase the current. It's actually possible to build a transformer without the iron core and instead just have two coils next to each other. However, the iron core allows much more power to be transferred. So we can draw our previous primary winding again, but this time using physics notation. The physics notation for a coil is to consider the current going in a certain direction to say the current is going away from us or towards us. So to explain this, we consider an arrow. And it's an arrow with some feathers on it. So when an arrow is coming towards us, we see the circle head and we see the dot point. So that's when it's coming out of the page. Or when it's going away from us, we see just the back of the arrow, which is the cross from the feather. So that's called into the page. So if we scroll up and look at our previous drawing, you can see that on this side, the current's going into the page because it's going this way, and then on this side here, it's coming out. Then it's going in, and it's coming out, it's going in, coming out. So if we draw that using this notation, we'd have all our out of the pages on this side and into the page on this side. So our magnetic field will look something like this. It's going up through here and it's spilling out and making its way around and back in. And it's making this sort of circle around each side. So this is sort of our north, and this is our south side of the magnet. If we draw our other coil, you can see that current's going this way, so this part is coming out of the page, this is going into the page. Out of the page, into the page. So we'd have out, 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 and this is in, 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 in. And so the magnetic field from this primary winding will spill some of its magnetic flux through here, which is what's able to generate the current on the secondary winding. So what the iron core does is it provides a good path for this magnetic flux, so it's not just going through the air. So when you're drawing a circuit with a transformer, the symbol is generally a winding, so you get a primary, secondary winding, and usually if it's an iron core, you'd put two lines through there to indicate the iron core. And you can simply draw a transformer as two coils overlapping. You can also put the polarity on the drawing, which will indicate which way the current's going to be coming out of the secondary. So if you consider our first drawing, you can see that if you move both coils to the same side of the transformer core, the coils were in the opposite direction. So this causes the output current to be in the opposite direction, or if you like, a 180 degrees phase shift. So on a drawing, that would look like this, where these little dots are your polarity. So this 180 degrees phase shift means that your primary, if it has an input like this, will result in the secondary having an input which is 180 degrees out of phase, so each point is the opposite. However, if both your coils were in the same orientation, that means that you've got your polarity set like this, then your primary will look like this, and your secondary will just be the same thing. As a final note, I'd like to mention some of the more practical aspects. Generally, transformers which power your house or ones larger than that would have its iron core and windings placed inside insulating oil. These are generally known as oil-filled. So this provides isolation to prevent arcing between different parts of the transformer. And you get arcing inside a transformer because there's a lot of different voltages. The top part of a winding is different to the bottom part of a winding. This part is different to here. This part's different to here. And that can depend on your input and the number of turns you have. The windings themselves are insulated so that you can't have arcing between these two parts or these two parts. Otherwise, if these were all in contact, it would be one big wire. Or if there's a little gap, you'd get arcing, and that will eventually destroy your transformer. And finally, the iron core of the transformer wouldn't be one big chunk of iron. The transformer is made of thin sheets which are laminated together, but insulated from each other. So you've got heaps of sheets of iron stuck together. And this reduces something known as eddy currents. So if you had one big chunk of iron, you'd have these eddy currents or circulating currents flowing around it. And this leads to losses. So if you have your iron core and you laminate it, then you only get little eddy currents. And this reduces the losses of your transformer. So that's it from me. This video provided a very basic introduction to how a transformer works. I'll also be making a more detailed video into the transformer's losses and its applications. If you have any questions, post a comment, please subscribe and visit the website. Thanks.